Hello everyone, we're going to talk about the root test now, and I just discussed the ratio test a little bit, and I wanted just to say that they're very similar when it comes to the technique of what we're supposed to do. So we're still going to find a limit as n approaches infinity of our series, and we're getting some value. In this case, we have it as an m. For the ratio test, we had it as an r. We've had it as an L before for the interval test. So really doesn't matter. We just want to find what the limit of our series is. And just like the ratio test, if our limit is less than 1, then our series will converge absolutely. If it's greater than 1, our series will diverge. And if m is equal to 1, then we have chosen the wrong test. So it's very easy to identify when to use the root test. Okay, so with these two examples, we can see that one way that's easily identifiable on when to use the root test is that we have both of these things being raised to the nth power over here, and then exactly the same thing with this. I've got two functions that's being raised to the nth power. It may be easier to see example number 11 if I just rewrite it for a second, so you guys can see that it's the sigma positive infinity of n equals 1, and then I'm going to go ahead and write e squared over n, all raised to the nth power. And so now you can see, just like over here, we have a function raised to the nth power. I will say really quickly that sometimes students actually mistake this for a geometric series, and one of the things that's clearly not a geometric series is that we have a variable inside of our parentheses, which means that this is not a number, so it cannot be a geometric series. So let's actually look at how we can do the problem now using the root test. So the first thing is we're going to go ahead and write a limit as n approaches positive infinity, and then we're going to go ahead and write e squared over n, all raised to the nth power. And so what the root test allows us to do is actually take the nth root of this entire function. And so this is actually pretty awesome for this to occur, because when that happens, then we're just going to get the limit as n approaches infinity of e squared over n, right? Just the limit of e squared over n. And so this is just a number over a variable, then this is actually just going to give us a limit of 0 because we're bottom heavy, and so this is less than 1, and again this is the m that we were finding earlier. Since this is less than 1, I can now say that this series is going to converge absolutely. So not too much work for this particular problem. So hopefully that does make sense. So if we look at this next example right here, we can go ahead and do the limit as n approaches infinity of the natural log of n over 2n, all raised to the n. And just like in the previous example, we can go ahead and take the nth root of this, and we're left with the limit as n approaches infinity of the natural log of n over 2n. Alright, so then we have to solve this limit, and this is a classical L'Hopital limit, because this is going to approach infinity, this is going to approach infinity. So if we take the derivative of the top, we get 1 over n, and we take the derivative of the bottom, we get 2. And so we're going to get the limit as n approaches infinity of 1 over 2n. And so we, again, just like with this example over here, we have that this is approaching 0, right? This is going to get bigger and bigger and bigger. So our limit is going to be 0, which means, again, that it's less than 1. So this series will also converge absolutely. Alright, so I hope that makes sense to you guys, and I'll see you guys in the next video. We talk about the alternate series test.